you for coming for the Don Sill Awards lecture. It's my pleasure to introduce Provost Amir Davirian on the podium to welcome you all.
Good morning, everyone. Good morning. Welcome to the fourth L. Don Shield Excellence in Scholarship and Creative Activity lecture. Before we start, I want to tell a story. You know, in 1980, when Don Shield was his last term, is when I came from Troy High School and took a course at Cal State Fullerton. So he is my inaugural president to the campus, coming to the campus. So Don Shield has a special memory in my heart. And so whenever I see Don Shield's name, that comes to my memory of this little kid walking across the State College, coming across and taking a course. So the award is presented to a faculty member each year for their excellence in research and scholarly activity and commitment to the educational mission at Cal State Fullerton. The award namesake served at Cal State Fullerton's second president from 1970 to 1980. He went to SMU in the spring of 1981. He actually was our president for 10 years after Dr. Langsdorff. This year's lecture is delivered by 2023 Don Shield Award recipient, Dr. Bogdan Suceavă, Professor of Mathematics. Please join me in thanking Dr. Suceavă for showcasing Cal State Fullerton globally through his outstanding research work that supports our core mission at Cal State Fullerton, emerging national model for supporting student success through innovative high impact experiences and co-curricular experiences, including faculty, student, collaborative research. I'm glad you're all here to learn from him the work he does as a proud Titan. Thank you.
Thank you, Provost Davirian. Now it's my pleasure to invite the Senate Chair, Dr. Matt Jarvis.
Fellow Titans, as Chair of the Academic Senate, it is my distinct privilege to welcome you all to today's lecture featuring the recipient of last year's L. Don Shields Award for Scholarly and Creative Activity. As an aside, when we created this category in the Senate for scholarly and creative activity, I don't think we had Dr. Suceavă in mind. We were sort of doing scholarly creative activities, what some people do, creative activities, what others do. I don't think we were quite anticipating the Bogdan Suceavăs of the world doing both of them. For making the award so aptly named, thank you, Dr. Suceavă. Today, we have the opportunity to delve into the work of a Titan in their field, whose dedication to scholarly excellence and creative activities has left an indelible mark on our academic community. In the pursuit of knowledge and innovation, Cal State Fullerton stands as a beacon of intellectual curiosity and academic rigor. It is through the tireless efforts of individuals like Dr. Suceavă that we continue to push the boundaries of discovery and understanding. Today's lecture is a celebration of his remarkable achievements and a testament to the importance of fostering a culture of innovation and exploration within our community. As we listen to his insights, let us be reminded of the importance of curiosity, perseverance, and collaboration in the pursuit of knowledge. On behalf of the Academic Senate, I extend my warmest congratulations to Dr. Suceavă for his outstanding contributions to our university and to the broader academic community. Thank you for joining us today as we embark upon this journey of discovery together. Welcome, and let us embrace the spirit of intellectual inquiry that defines our university's mission. Thank you.
Thank you, Dr. Jarvis. Now it's my pleasure to introduce the speaker of the day, the recipient of the university's 2023 L. Donald Sills Excellence in Scholarship and Creativity Award, Dr. Bogdan Suceavă studied mathematics at the University of Bucharest, 1994, BS, 1995, MS, and at Michigan State University, PhD in 2002. Since 2002, he has worked at Cal State Fullerton, where he wrote the majority of his over 80 research papers in mathematics. His expertise lies mainly in differential geometry, but his works explore analysis, algebra, and the history of mathematics, including several chapters of geometry, from axiomatics to metric geometry. Besides his scholarly work, Dr. Suceavă authored 19 literary volumes in Romanian, essays, novels, short stories, and poetry. Some of his literary works are translated into English, French, Czech, Hungarian, Turkish, Korean, Bulgarian, Italian, German, Swedish, Slovenian, Croatian, and Dutch. He is one of the recipients of the 2020 MAA Korea Award for expository writing for a paper written with Klesser, Adam, E.M. Rathbun, and I.M. Serrano. In the fall of 2011, Dr. Suceavă established the Fullerton Math Circle, an outreach program of our Cal State Fullerton Math Department, focused on developing problem-solving skills in mathematics for K-12 students. With this, without further ado, I would like to invite Dr. Suceavă to the podium for his tonsil lecture.
So I'd like to thank very much to the scholarly community at Cal State Fullerton for recognizing the values that the math community actually are representing in our campus. And that's another way of saying that in a campus like ours, it's particularly important how we present mathematics to our community. And if I told you that the PDF is frozen, what would you say? Okay, so I would like to thank the math department at Cal State Fullerton, where I've been since 2002. And I'd like to start on these slides with a longer list of thanks, including Michigan State University, which back in the days in the 90s, end of the 90s, they had a fantastic intellectual atmosphere. That was really something special. And I spent 6 amazing years there. I have only good things to say about them, as well as about the University of Bucharest, where I had top-class conditions, in the sense that the classes they had at that time, they were absolutely amazing. We had classes that were running for a sophomore level that today are graded topics in our schools. And a special kind of thanks to the American Math Society. What's going on with that? So American Math Society is, I would say, the top matrix where my schedule goes. I'm looking first at the calendar of events in terms of editorial opportunities, conferences. And by the way, I think I owe my job to AMS. It's a story I have to tell in a few minutes. And not only that, but there is also MA, because in the mathematical community, we are blessed with many societies. And in the US, there are at least 2. There are more. There is CIAM and AWM, but I wasn't that much involved with them. The Mathematical Association of America has wonderful local conferences and journals. I'm interested in them too, okay? And last but not least, the first academic society I've seen at work, it's something small. It has only about 8,000 members from what I know, but they do something special about K-12 education. And I'd like to elaborate on that in a few minutes. So this is where my thanks should go. But then there is the math department. And let me put it like this. I love everybody in this picture and everybody who was hired after this picture is taken. And I love Dr. James Friel, who's right here. He's not in the picture, but I love Dr. Friel. So, and special thanks to my friend and my therapist, Professor Stephen Good, who's right here in red shirt in first row, right? And let me tell you more about the AMS. So we see here, I'm going to use this mouse. That's the student poster session at the joint mathematical meetings right before the pandemic hit. That's in January 2020. And we have like over 300 posters in display, right? Perhaps you don't know, but the very idea of poster session at the national conference originates at Cal State Fullerton. And it was an idea circulated in the AMA community by Mario Martelli, by the late Mario Martelli in the time when he was a faculty member here. So we are it, right? So in this picture, we see here Alex Luna, who I believe very soon will defend his PhD dissertation at UC Irvine in mathematical analysis. In this particular picture, he's presenting a poster that he worked with my friend and colleague Zairi Bragimov. So there have been JMMs where we contributed, we meaning the family at in the math department, with 11 posters, 12 posters, 13 posters was the maximum as far as I recall. And I think this is important. Some of these posters are actually also publications, some of which are high impact publications. And that's the atmosphere that I was referring to about American Math Society, okay? And my first encounter with Cal State Fullerton happened like this. I went to the JMM and I delivered a talk in the geometry session. And in the back of the room, it was a full house like about today. And he was this guy. And apparently I applied for a job at Cal State Fullerton and the file landed on his desk. And he told me something that would capture anybody's attention. He told me I make sense. And of course, he debriefed me like secret information kind of style, took me outside and interrogated me everything I have in my plans for my life and so on, and somehow checked all the boxes. And that's why I'm here, right? That's Boreal Klassen. Now, what mathematicians do, okay? Mathematicians write papers. Okay, now, honestly, 2002, I was about here in my career. So this is a database of the European Math Society. It's called Centralblatt, and it actually counts how many papers you do per year. Now, good or bad, most of what I did happened at Cal State Fullerton because it's this. But before, there was almost, I mean, it wasn't that much. When you hire somebody at this point, maybe he will never write anything again. But if I remember, I think I promised a few things, and I don't know, did I do it? Did I do it? No, yeah. Yeah, because everything I said at the time sounded like fairy tale. No, it's possible, and the reason why it's possible is because of the atmosphere and the environment and the structures we have in our campus, okay? And let me prove this statistically, okay? So this is the list of my co-authors according to Centralblatt. Now, I wrote a couple of papers alone, but here are my colleagues. It's Nick Brubaker, it's Adam Glesser, who today he's teaching so well that we had to take him away from teaching. So it's Al Agnew. We published together in Historia Mathematica. We are not historians of math, but we did it. It's difficult to do that. And then my friends Roberto Soto and Anael Verdugo. Anael Verdugo actually helped me do something that I wasn't able to do alone, and I think it was important. And then there is what do we do with Jolene Fleming? Because she was my first research student, and now she's my colleague. Let's count her as faculty, as well as Zairi Bragimov mentioned before, Matt Radbourne, and that's about it. And then most of the other names you see here are actually undergrad students at Cal State Fullerton, my co-authors. And I would like to to express my special thanks to Charlie Conley. Charlie, where are you? Oh, Charlie Conley right there. Who's actually, we wrote only one single paper together, but he's the current record holder in terms of Putnam points for Cal State Fullerton. So he scored a total of 72 points in 3 editions of the Putnam competition, which is huge. And then the maximum is 39 points. Charlie. And it was a great pleasure to, I'm gonna say a couple of things more about our paper later on. He's somewhere here on the list, right here. And my most recent co-author, Dui Tran, who unfortunately is not here yet. The database didn't pick you up yet, but it's coming, I promise you. Dui Tran, thank you very much. So one more time, the claim was the fantastic atmosphere that we have in our campus, because if you are in another place where this is not appreciated, why would you even do it? But that's what happens at Cal State Fullerton. So my goal was to explain what mathematicians do. Here it is. All right. And then most of the papers I wrote with this guy speaking here in a conference in Japan. And I think we wrote 22 papers, if my reckoning is correct, but Central Blood didn't pick them up all. And he's right now known for this book, which is ranked among the best in relativity by Book Authority. So he's well known for, I don't know what's going on. This appears in the series in physics. He's a mathematician, a very good one. Now, a little bit of personal history, like explaining where I'm coming from, and this is gonna require a little bit of decoding. That's an old pic from the summer of 1990, and I am here. Okay, it's a younger version, and I'm not a high school student in this pic anymore. I'm an undergrad student, I'm a freshman, and I've been invited by the Society of Mathematical Sciences to work as facilitator for summer school. And I got in May my homework to present a 2-hour lecture on complex numbers and a 2-hour lecture on integration. Okay, now, what I didn't know is what I'm getting into, because let me tell you who was the audience. This guy here is today Ioan Bejenaru. He's a top-class PD expert at UC San Diego. Gențiana Danilă, she's right now at the Jussieu Institute in Paris, University of Paris. Adela Vraciu, she's at University of South Carolina. And Marius Kreining, he's a kid, but later on is a recipient of Lishnerovitz Prize in geometry. And these are a few. So basically, you're preparing 6 problems, and you have to have a few hours in the back of your pocket, because they burn through your content immediately. You put the problem on the board and it's done. So you're calculating your time very carefully. You said 6 problems it is. It was 9. And at the end, it was like, the content was okay. We could do them. I felt terrible, but then I learned my lesson. And who brought us together? Nicolae Todorescu is right here. He is one of the 3 scholars who actually came up with the idea of International Math Olympiads back in the 50s, when it was kind of difficult to discuss between different schools of mathematics. And I don't know, he managed to make it work. I don't know. He was an inspiration, and I'm very grateful to his memory for inviting me that summer, because I learned how to do it. And it's like this, I actually took that model, turned it into something that works in California. And if the original inspiration was actually rooted into what the Romanian and Hungarian schools did, very recently we started to import problems from our mathematical cultures, especially China, Japan, Vietnam, and there is a lot we can do further. Here's why. Because there is so much talent in California, you wouldn't believe it. And suddenly, this is our problem, because we can mine for gold. All right, so what's going on here? The Zeng brothers interviewed by the Orange County Register, and I think we had a total of about 4 materials published by OCR in the last 12 years. Pretty much, if it wasn't for the math department, OCR wouldn't have content. They wouldn't. That's just. Actually, this whole idea was discussed extensively with Stephen Good, and when we decided to start it, I said, you know what? Unless something is getting broken, and I will never stop. And things got, yeah, it's complicated. I will stop right here with this story. But hey, math circle. What is the theorem? The theorem is the following. We can actually use the environment we have, because here in the picture to the left, we have a statistics student, Tabar Daoud, who right now is a PhD candidate in statistics at UCI, who worked at that time with Sam Besetam, and she's getting trained how to teach. Okay, it takes you about a week to get everything right, but hey, if I can do it, she can do it. Here's Melissa Riddle, who's right now working as a data analyst, but she learned how to teach as well from training that we provided with the math circle. And the picture here, it's a very special one. So we have my friend and colleague, Jessica James, introducing a 10th grade student. The name is Sushant Satish Kumar, who right now is a math major at UC Berkeley, who came and delivered the colloquium talk for the math department. High school student, what can a high school student tell? He had 20 plus problems solved from the American Math Monthly. Now, with all due respect and love, I challenge everybody from this room to do that. The kid can do it. Okay, the only thing I did is tell him that the monthly is important. And then, him being a super processor, so in the last 10 years, I think we had 5 high school students delivering colloquium talks for the math department, including Alvin Kim, who's at Johns Hopkins, Kevin Du, who published a paper in the College Math Journal right before the pandemic. You hosted it, my friend Scott Anning. And then this is the quality we have. Presently, the math circle is in the great care of my friend and colleague, Sho Seto, who mentored the most recent paper will appear in Dimensions this spring. So it's a paper on Maclaurin series written by an 8th grade student. Okay? Therefore, the theorem. The math talent can be identified early, and that was the proof. The students can be introduced to certain elements of algebra and geometry. Don't do calculus too early because they don't have to explore the technical content. It's important when you introduce each one of the concepts. You have to find something that's called age-appropriate problems. And because we have those almost 500 math majors, you could serve them best if they have a place where to practice, if they're interested in training amazing students. All right, and then we are a public university. By the way, what does this mean here in this context? Well, it kind of, if there is anybody gifted on a radius of 100 miles from here, is my problem. I keep saying that and everybody goes like, why do you care? What if it's somebody of Ramanujan caliber? I care. And then some of the math circle students joined top academic programs in the US, and I think these guys, they owe me cookies because, you know, the students are going there and they score in the Punam competition for UC Santa Barbara, UC San Diego. But then it was a bunch of students who went to Yale and Princeton and Caltech. Therefore, talent exists in our neighborhood. And quite a few of them are coming from Troy, that's true. It's fantastic pool. So, and by the way, I forgot to mention, this is not what I do for my living. No. This is what I do for pleasure. So this is, I'm not paid for it, right? So I don't want to give you the fairy tale version about Romania. I want to tell you the whole story, which is actually something like this. That's how the university library ended up in December '89. And the pics are done by an amazing artist who happened to be on the field there. And let me put it like this. I appreciate a lot places that are peaceful and quiet, where you can do the work and nothing like this happens ever. And if I were to talk about the amount of trauma and the stress that's coming with the aftermath of such events, that'd be something I will never end. Okay. And what did they do with the library? Pretty much friendly fire through the building. And it burned for 2 days and 2 nights. I happened to be in the neighborhood and see it, so promise you it's true. And then I happened to write about it. And there is this journal that Springer Verlag has. It's called the Mathematical Intelligencer. And in the Mathematical Intelligencer, they publish stuff about the lives of mathematical communities. And I was impressed to see that they actually published a piece that I sent, where I describe among the other episodes the story with the library burning. And that was actually a fragment from an essay that I published back in a few days ago with a publishing house in Romania called Polyrom. And part of it is actually starting with manuscripts that are lost. Okay. And actually, the stories that I've been writing about, it's not that I insist on writing stories and poems and so on. It's just that you want to convert all the experience or the personal experience that you've been through and tell the story as it was. It's a way of shaping the trauma in a positive direction. And for example, this novel was written when I used to have a small office that didn't have window, and I have to confess I wrote from time to time in the McCarthy Hall. Most of this was actually written in McCarthy Hall, and it was about an episode that happened during the Romanian Revolution, and I had to tell the story. It was like I couldn't go on without doing it. But if you are not an algebraist at some point in your life, you don't have a heart. I started in algebra back in the last time when we met, I said that algebra doesn't exist, right? So I'm willing to say anything just to make you laugh. So when I was 17, I considered the following problem. Determine the smallest number of cycles of length 3 in which you can decompose an even permutation. And later on, I turned this into a problem in the monthly, and when somebody, great problem solver, came up with a proof, I couldn't understand it, and this is how complex the problem actually was. And that's what I was doing in high school. Then a few years later, I figured out that surfaces and hypersurfaces exist. And my first paper was written at a time when I was not really as familiar with English, not at all. And the deal is this. I learned as an undergrad student that actually working on hypersurfaces is a good training ground for undergrad research. You don't need tensor calculus, you don't need much, you don't need even the Riemannian structure, you don't need anything, bare hands, and you can actually investigate content. That's a good training ground. No, thank you for agreeing with me. So that's okay. Coming from you, it's good. And one of the books I read when I was in my undergrad years, there used to be the library of the Institute of Academy that was located in the math department. So you had the best books right there, just to buy. And one of the books was actually coming from Leningrad. And for a couple of chapters, there was this superhero who was proving everything. The name is Bang Chen. And I started to look for his books and his papers. The matter turned into obsession, mathematical obsession. And then I thought about, how about if I actually going to do my thesis there? And this made the matters very easy because before I landed in mid-Michigan, I already read a couple of his books. And let me tell you where these books are coming from, because that's another story right there. So that's the original. Now it's a Dover paperback. Anybody can order it and read it. It's the aftermath of John Nash's embedding theorem, which is shaping a theory of subspaces. That's what's going on. And you wouldn't believe it how many citations this book had. The funny part is this was actually written by somebody who is 29 years old. It requires a lot of vision, a lot of mathematical culture to actually accomplish such a feat. But my favorite math book is this one that he wrote in 1984. And this is as good as a crime novel. It's like, who's guilty of everything like this? And that was the Laplace operator. You're investigating spectral geometry, and it's a study of it. Now, my apologies, I should be referring to the most recent edition, but this is the one I read, and I found it amazing. So, who was my doctoral advisor? He was actually coming from Taiwan, from that interesting atmosphere in the 60s in Taiwan. They didn't have PhD programs, but they had funding to invite scholars from abroad come and lecture. And this is Bang Chen, the version that's very, very, very young, before coming to the United States. This is his first professor in differential geometry, Tsinghua Tang. And then Tadashi Nagano. Tadashi Nagano was an incredible geometer who spent a semester in Taiwan, and then he ended up by discovering Bang Chen, which is not hard because he was brilliant. And then she suggested him, why don't you come and prepare your thesis at Notre Dame University, which pretty much ends with the following situation. So suppose there is a football game between Notre Dame and Michigan State University. And of course, I'm totally Spartan, and I'm inside, I'm green and white and so on. And Professor Bang Chen supports Notre Dame. That's the situation we're in. So anyways, this picture was published first this week because we edited a journal called International Electronic Journal in Geometry, which appears on a server in Turkey. And I had to write his biography for this particular event. He turned 80. And I begged for a couple of pictures from the 60s. And he gave me this piece of gold for the editorial. And I was like, oh, this is a document, actually. That's interesting. And this is the same characters, Tadashi Nagano and Bang Chen. If you're looking at the date, it's like December something 2001. It's about the time when I was actually doing that file that landing on Vodil Klassen's desk. And Professor Chen was in Japan, and I was applying for jobs. That's the situation we're in. Anyways, so what is the problem? And now I apologize, I'm going to have to do a little bit of math just to describe what's going on. And I'm going to use as a subject of my investigation a submanifold, that's this smartphone. And I want to understand when this can be placed into an ambient space like that. Sometimes it doesn't fit. Let's see how. So the problem was actually very old. It's about 100 years old. Given a Riemannian manifold, can we embed it into a given ambient space? Now, the Riemannian manifold, it's the math slang for the idea of space, like the old idea of space, like in Plato's philosophy. The manifold appeared in 1854 due to the efforts of Bernard Riemann in response to a challenge from Carl Friedrich Gauss. The problem of embedding originates to Élie Cartan and Maurice Janet. And Nash's embedding theorem was that given every Riemannian manifold, you can actually embed it into some Euclidean space of dimension sufficiently large. Like if this subspace doesn't fit in this particular ambient, I can go and ask from the dean's office for more dimension, and in dimension maybe 17 or something, maybe it would fit. That's how it works. So then the problem is, what is the best possible embedding of a Riemannian manifold into some ambient space? Like, can you have like a perfect fit? The perfect fit things. How do you find the best possible embedding? And that's actually at every point, the tension should be minimal. And you have to think a bit what tension means in terms of distance. And I'm going to play a little bit with the idea of a surface. So suppose you have a surface and a point on it. Take the tangent plane and a normal to it, okay? No corners allowed. Everything has to be smooth. Then you're taking the planes passing through this normal direction, and they generate some intersections with the surface. They are called normal sections. And for them, we can calculate the curvature due to a formula that's actually inherited from Isaac Newton's time, you know, about the time when he proved that planets move around elliptical orbits. Well, let's denote by kappa 1 the smallest of these curvatures of planar curves, the normal sections, and by kappa 2 the largest, okay? The curvature for a surface can be calculated patiently just by doing the product. And the arithmetic mean gives the mean curvature, and it was not obvious. Like between the invention of kappa and the introduction of H took 4 years. It's not really obvious how it came out. It's a long story there. But what we're interested in for the geometric quantities is the balance between the quantities that are described in the subspace and those that describe the ambient. And actually, if you want to apply Nash's embedding theorem, what you need are relations between the two. And the bad news is that there are not many. And yet they have to go through certain equations, and you have, in a very intelligent way, investigate this relationship. So Carl Friedrich Gauss, 1827, proved that capital kappa, the Gaussian curvature, is intrinsic, depends on the subspace, while H, the tension like H, depends on the ambient. That's how it is. Sophie Germain introduced in a memoir from 1831, the year when she passed away, she introduced the mean curvature due to physical considerations. So we're interested in relations between intrinsic and extrinsic. That's the game we play. And actually, that's the idea that brought me to Michigan State. I was interested to learn how to do that. And now, again, a meta story. The question is, how do you have so many ideas for projects with undergrad students? Fortunately, we don't have a complete list of these relations, and there is more to explore. So all it takes is just patience, ideas, and willingness to look into the problem. Now that you have the vision, and due to John Nash, you learn how to do it, just explore. And it requires a little bit of craft, because you need to consider quantities that have physical motivation, and you could eventually find something about them. But oh boy, this requires also time and dedication and so on. So let's play around, and let's show how we can generate a very simple relationship between something intrinsic and extrinsic, okay? So again, who's kappa? Kappa 1 and kappa 2. H is the arithmetic mean. No square is negative. FOIL out and arrange the terms in a way that you retrieve the Gaussian curvature and the mean curvature. So H squared is more than kappa. All right? Now, when do you have equality? You're going to have equality when this square vanishes. That is when kappa 1 equals kappa 2. We call these points umbilics in differential geometry, and they have been studied since, I believe, 1830s. All right? So let's start to color them with Titan colors. Extrinsic versus intrinsic, that's the business we're in today. And why do we care about that? Well, a surface is minimal if it doesn't have any tension. You know, there's some people in the world who don't have any tension with the ambient they have in, and some people who have a lot of tension wherever they go. You know, so this is the same about surfaces. And a surface is minimal if H is 0. Now, what can I do to stop this H ever vanishing? Well, I can ask this kappa to never vanish, to be strictly positive, bounded away from 0. So that's a way of stopping minimality. And you are providing now a Riemannian obstruction to minimal immersion. That's the game. So I said that. a classical theorem in the geometry of surfaces, which, by the way, is kind of hard. If you have a compact surface, then there exists a point where the Gaussian curvature is bounded away from zero. Based on the above abstraction, we just proved that the compact surface in R3 cannot be minimal. Okay. By the way, this is you don't want to put this on the final exam in Math 425. That's don't do that. So I tried it on humans, and it's not what you want to do. So the problem we're in, get more relations like this. Could we? All right. Now, there is a book that's like 500 pages and so on. And I've seen it being written in the last 30 years. It's a great pleasure to have a monument like this with us. But good news, there is more good for us. So how the whole story started. The sectional curvature, so you're in something of dimension n, and you have a metric on it, and the sectional curvature goes on the planes around the point, right? So how about you're trying to investigate infimum and supremum of all possible deformations in that planar direction? What can you do about that? So one of the theorems published by Bang and Chen in '93 that caught my attention was the following. Infimum of the sectional curvature is more than a bunch of terms, and you just have to see how to read this. So a space form means a space where sectional curvature is constant. Just imagine a sphere. Imagine you have a basketball in dimension as much as you wish, right? And how about we perform an estimate of that? That's not clear yet. Let's rewrite it. So terms that depend on the ambient in blue, and terms that depend on the space in orange. Okay, homework. Can you come up with more relations like this? And why is this important? This is important because it also emphasizes the case of equality. The equality in this particular case gives you the best possible fit of that subspace into the ambient. That's what you want. You want to characterize the best possible embeddings. And that's the answer to the Nash's question. So that's the reference. Now, let's try to turn this into an undergrad research project, as philosophy, as spirit, as game. And the way it works is pretty much like this. You take your friends in the room 476, and you lock the doors, and you tell them this. I have a conjecture. How about we're trying to prove this inequality? If you agree with me, you can go home. We did that, right? Yes, that's yeah. So hypersurface is the generalization of a surface. The ambient has dimension one more than the hypersurface. What if we're looking at, how am I doing with the time? I have like 30 more seconds, right? No, I'm just starting. This was just warming up. So if you're looking at the quantity kappa over h, careful, don't divide by 0, okay? This is something inspired from the geometry of helices. And, sorry, okay? How about we are introducing the following quantity? You're taking something that looks like the sum of the harmonic means measured on the faces of an anhedron, and then you normalize it. Okay, anybody can introduce any quantity like this. But what can you prove about it? Why is this natural? Why do we care? Well, you got to prove something, otherwise you don't have anything. So, but first, the equality case. What if we introduce, instead of the umbilics, we're talking about absolute umbilics? There is some important property, the fact that the Gauss map is conformal at those points. But I don't know, explain. I mean, there are some physical reasons why this is interesting. Let's play around and let's look at surfaces where absolute umbilics might exist. If you take any minimal surface, like, for example, the catenoid that intrigued Leonhard Euler in the 18th century, all the points on the catenoid are absolutely umbilical. On the cylinder, you stand no hope to find any. The totally umbilical hypersurfaces have absolute umbilics. How about the donut? Well, if you take a donut, can you find any absolute umbilical points? If you're trying to find points where the two principal curvatures are equal, you don't stand any chance. But for kappa 1 equals negative kappa 2, you do. And that is this green set that's on the hyperbolic part of the inside of the donuts, the one that you bite without touching, right? So right there, it's a there is a set that's of interest, okay? Then with this amalgamatic curvature we just introduced in McCarthy-Hall, we can prove this very nice inequality, and I like it because it doesn't have coefficients. You don't have to multiply by 2, by 7, or by whatever. It's a natural inequality. And honestly, it's in the extrinsic class. It's an extrinsic characterization of immersions. Sorry, it's not of that high quality that I was showing you in the 93 project, but it's something new. It was never considered before. Lucky us. And as I was telling you, Orange County Register, they would die without the math department, because when we published this in the Taiwanese Journal of Math, we made it. So what was that? 2013 joint math meetings in San Diego, right? And it was Lucio Odom, Rebecca Ednayer, and Brady Gardner, besides my friend Charlie here. And the reason why I wanted to talk about, I mean, I had 20 plus papers written with students, and quite a few of them high impact, but this is a group that was absolutely amazing, and the chemistry in the group was wonderful. I loved it. I wanted to mention this theorem. And a recent result that was proved with my friend Due Antran, who's right here. I think you presented it actually more than I did. Is this right? Yeah, so yeah. It's a relationship between intrinsic and extrinsic quantities. How do you generate that? Well, in the differential geometry world, there is a famous theorem by Ossian Bonnet and S.B. Myers, and it starts with a natural condition that the sectional curvature is bounded away from 0, all right? So here's what we said. How about you're taking a three-dimensional smooth hypersurface, the object of our work, right? And you take the Bonnet condition. Then the following holds. And that's really, by the book, a relationship between intrinsic and extrinsic quantities. It's exactly proof that there is more gold to come up with, okay? And the proof is not complicated. It's just FOIL. And recognize what the matters are. I think we have 5 theorems in our paper, which was published this week, right? That's your first paper, right? My pleasure. So, but where did the curvature originate? That's a question for Dr. Glesser, who's sneaking out. So it's good that he won't be here when I'm going to talk about him. Originates in a question asked by Julian Coolidge a couple of years before he passed away. That's one of the great American geometers, who said that the story of curvature is unsatisfactory. We don't know where this idea is coming from. And, you know, maybe it's Nicole or Emma, maybe. And, well, I kind of felt like it's ORM, and there is only one way to prove it, to actually read as much as possible from the original 14th century materials, except that I have no training in reading medieval materials, and it took me a while to figure out how these guys used to write in the medieval times. And here's what we found by really digging, that he gave the correct curvature definition for planar curves. He tried to apply it to understand 14th century level of understanding real life phenomena, which is quite intriguing. And then, among other things, he stated something that's equivalent to the fundamental theorem of curves in the plane, that the curve is characterized by its deformation. And the paper appeared in the notices of AMS. And I had the great pleasure on working on this with Isabel Serrano, who right now she's preparing the defense of her thesis in statistical biology at UC Berkeley. And let me tell you this, everything she's touching turns into gold. And I can't explain that, because if you ask me, go ahead and do something of the same quality as the work I did with her, I don't know. Okay. So this work was actually followed by 2 hours that I wrote with Anael Verdugo, because the problem was this. What is Nicolo Rem actually doing? Is this genuine applied mathematics? Can you actually quantify whatever he wanted to quantify in the 14th century? And actually we found that a few ideas in his work are genuine applied math topics that have been studied in the most recent 30 years. So Nicolo Rem was right, in a way. So over the years, I had 3 essays included in the best writings on math. And again, this is something I should say, thank you, Fullerton, because it happened as I had the opportunity either to teach history of math or to interact with my colleagues on various matters, like the problem with quadrivium. Now, again, this is not directly my problem. Why would I go to the realm of, Visigothic kingdom in Spain, 7th century and so on? The problem was that this was the greatest medieval bestseller, Isidore's Etymologies. There was the Bible, and then the next title that circulated in Western Europe was Isidore's Etymologies. And as a mathematician, I wanted to know what kind of mathematics is in there. And if you start analyzing, you get scared, but you have to write it decently and nicely. And I invited Lucy and Isabel to help me tame my feelings into a text that's acceptable for a decent publication. And this time it was very successful. So that's a Central Bar review written by a scholar from Russia, saying that he gave a summarized description of the quadrivium. That means 4 mathematical sciences: arithmetics, geometry, music, and astronomy, as understood at that time. And oh boy, they forgot the old understanding of those, as in the Greek Roman times. It was much deformed. Everything relied on Plato. It's the Plato's classification as kept in the 7th century. And the third essay included in the best writings on math was co-authored with Adam Glesser and our colleague from Chapman University, Mihaela Vujiac. And he was like this. I owe my job to Sophie Germain, because Sophie Germain invented H. And I couldn't prove those inequalities if I don't have H, right? And I wanted to really understand Sophie Germain, especially that study that she wrote in 1831, and all the essays she wrote back and forth. She was a scholar outside academia because, at that time, girls couldn't go to college and so on. But how about we read her today? And we started to investigate really what she said. And especially her vision on mathematics, the way she studied Isaac Newton, for example, it's in the essays. And we commented on that, and we analyzed what happened in the chronology of all her work. And that was also particularly successful. And that's an article that started originally from an undergrad research project for Isabel Serrano. But when I felt that this is a little bit more than that, I inquired with Adam Glesser and Matt Radburn if they would be interested to expand and elaborate. So it ended up with a paper that was recognized by MA with the Polya Award. But what I wanted to say is that this is not the first time that somebody from Cal State Fullerton gets an MA writing award, because 30 years ago, or when was that, 40 years ago, our older colleagues, Harry Schultz and Bill Gerhardt, got the same award, which is given for telling stories with mathematics in it. Therefore, the math department at Cal State Fullerton tells good stories about mathematics, and this is actually the seal. So what can you do? It's like this, go ahead and wait for your students in the breezeway, give them a problem, and then elaborate on it, and look what happens, all right? So this is what the mathematicians do. Now, not always a happy end. What if you're investigating the best possible embedding into a Keller space form? A complete classification of the equality case of that thing. That is not done. And, from time to time, I go back to this problem and I feel like it's, can I say as bad as Wilmot's conjecture and so on? Well, the Wilmot conjecture is solved now. It was proved in 2013. This is the paper that I think is my best, was written in like 2014. And I'm curious to see who will ever do more about it. And on this positive note, I'm just going to say one more big thank you to all. Questions, remarks, and complaints for Dean Johnson?